Thanks for clicking. Welcome to another Narculus production. Today we're going to be talking about position, velocity, and the acceleration functions. So you learned about all these in physics. So we're going to talk about how they can apply, or how calculus can be used to help us to calculate the position, the velocity, and the acceleration functions of a given expression. All right, so let's get started and let's see how we're going to go about doing this. So here's some general knowledge about things that you've learned before. The position function, which we normally call x of t, finds you the position of a given object at a given time t with units measured in feet, meters, miles, etc. So that's what your units would be. So that's your position function. It's usually labeled as x of t. Okay. Now, velocity, the velocity function v, right? Velocity is the rate of change in the position of an object. Okay, with units feet per minute, minutes per second, miles per hour. All right. Now, if we think about this, velocity is the rate of change in the position. Well, rate of change, that's a fancy way to say slope. We know that. Okay. And I want to find the slope of the position function. Well, I know how to find slope. Slope is the derivative, right? Slope means derivative in this class. So to find the velocity, v of t, you find the derivative of the position function. So the derivative of the position function represents the velocity. And you can kind of see where this is going here. The acceleration function, the acceleration a of t, is the rate of change of the velocity, okay, of an object. And the units are given in feet per minute, feet per minute squared, or meters per second, meters per second squared. That would be your units. Okay, your units are important here. You should know them. You should be able to write them. It also helps you to figure out some of the problems. Now, acceleration is the rate of change of the velocity. But rate of change means slope, and slope means derivative. So to find a of t, you're going to derive the velocity function. Or instead of deriving the velocity function, you could also derive the position function twice, right? The first derivative of the position would be the velocity, and then the next derivative of the position, or the first derivative of the velocity, is the acceleration. Okay, and that's the concept that we're going to use here to figure out what all these functions are. So again, we're back to the same thing here. Slope means rate of change means slope. Slope now means derivative if you want to calculate the slope at one value. So that's what we're going to do here. Suppose a particle moves on the x-axis, such that x of t is given by the function 6 sine, oh, that should be t. Sorry, folks, that's a typo. That should be 6 sine t plus 7. For x measured in meters and t in seconds. Find the velocity and acceleration of the particles at t equals pi over 3. So what I'm looking for is what we call the instantaneous velocity or instantaneous acceleration. The velocity or the acceleration at one moment, one instant in time. Okay? I want to find it at t equals pi over 3. So I'm looking for v of pi over 3, and then I'm also looking for a of pi over 3. Well, I can find those. I know the position function, so I'm going to have to derive the position function. If I do, it gives me the velocity function. So I need to derive 6 sine t plus 7. The derivative of 6 sine t is 6 cosine t. The derivative of 7 is 0, so that drops out. And now to find the instantaneous velocity at pi over 3, I'm going to find x prime of pi over 3, which is really just the velocity of pi over 3, which is 6 times the cosine of pi over 3. And now I'm going to go on that unit circle that I know so well and find 6 cosine of pi over 3. Cosine's the x coordinate there at pi over 3, and that would be a half. So half of 6 is 3. Okay. Well, 3 what? We're talking about velocity, and we're measuring in meters and seconds. So this is a measure of meters per second. That's my velocity at pi over 3. At this instant, when t equals pi over 3, the velocity is 3 meters per second. And now I want to find the instantaneous acceleration, or the acceleration at pi over 3. So to do that, I would have to find the second derivative of the position, which is really the first derivative of the velocity. So the derivative of 6 cosine t will be 6 times, the derivative of cosine is minus sine of t. So that's negative 6 sine t. And now I'm going to find, v prime of pi over 3, which is really a of pi over 3. So that's negative 6 sine of pi over 3. And negative 6 times sine of pi over 3 is root 3 over 2. Cancel out the 6 with the 2. Makes negative 3 root 3. And my units, acceleration is measured in meters per second squared. And there's my answer. That's the representation of the instantaneous velocity and the instantaneous acceleration at pi over 3. Okay? So it can be that simple. All right. Now, let's talk about what we would need to know to answer some of these questions. So we have 3 functions that we can work with. We can work with x of t, which is the position function. We can work with v of t, which is the velocity function. And a of t, which is the acceleration function. So if I wanted to know when the particle is stopped, so again, this is all stuff you should have learned last year in physics. To figure out when the particle is stopped, I would need to know when the velocity function is equal to 0. When is the velocity equal to 0? When am I not moving? Okay. When is the particle moving up or to the right? So it could be either way. It can be written either way. It could say, when is the particle going up, or when is the particle moving to the right? Either way, they mean the same thing. One is just in terms of the x-axis. The other is in terms of the y-axis. But the concept is the same. To figure out when the particle is moving up or to the right, you need to know when the velocity function is positive, right? Where velocity is greater than 0. Okay? When the particle is moving down or to the left, you would need to know when the velocity function is less than 0, when the velocity is negative. Okay? The velocity is positive, or here where the velocity is negative. When does the particle change direction? Okay, for the particle to change direction, right? Let's say you're going up and down. Okay, so if something's moving up and down, it's moving up, it's moving down, it's moving down, it's moving up, it's moving up, it's moving down. So I would need to know, and where does it change direction on this picture? It changes direction there, changes direction there, changes direction there, and changes direction there. So what would I need to know? I would need to know when this is going up and then it's going down. So where it changes from moving up to moving down, or moving down to moving up. So I would need to know when the velocity changes signs. So if the velocity changes from positive to negative, or negative to positive, right? Because that's where something can change sign, where the velocity changes from positive to negative or changes from negative to positive. Because if the particle is moving up, the velocity is positive. When the particle is moving down, the velocity is negative. So it changes direction, whether it changes from going up to going down or going down to going up. That's another way to change directions. All right. So you would have to figure out where the velocity changes from positive to negative or negative to positive. To do that, the first thing you would have to do is figure out where the velocity is equal to 0, right? Because that's the point. Think about it. You're on the coordinate plane. 0 is the place where you would change, where something would change from negative to positive or positive to negative. 0 is where it would cross over. It doesn't have to cross over. It may not. That doesn't cross over. Okay, this point here, it doesn't cross over. But this is where it would cross over. All right. So that's the first thing you'd have to look for. Okay, so let's try. Suppose a particle moves on the x-axis such that x of t is given by this expression for x measured in meters and t in seconds. The first question is, when is the particle stopped? When? That means time. So I would need to know where the v of t, the velocity, is equal to 0. To figure that out, I need to find the velocity function. So this will help some of you to remember it. We're remembering this lesson as PVA, position, velocity, acceleration. Position is your first initial function. Velocity is its derivative, and the derivative of velocity is acceleration. So I have the position function here in my slide here. X of t is given. So I would need to find x prime of t to get the velocity function. So I'm going to leave the 1/3 out of it. The derivative of t cubed is 3t squared. Minus 7 over 2. The derivative of t squared is 2t. Kind of see what's happening here. The derivative of negative 6t is negative 6, and the derivative of 5 is nothing. So those 2's cancel, those 3's cancel, and it leaves me with a velocity function of t squared minus 7t minus 6. To figure out when the particle stopped, I would need to know when the velocity, which is that, is equal to 0. So now the question is, what would I do with this? Well, I'm going to factor it. Okay, it's quadratic. So factor of t and t. The two numbers have to multiply to be negative 6 and add up to negative 7. They're going to multiply to be negative 6, add to negative 7. No, that's not going to work. So let's change this slightly. Sorry. Make that a plus, make that a plus, make that a plus, make that a plus. There we go. Now they got to multiply to be positive 6 and add up to negative 7. Well, that I can do. Make them both negative. And then I'm going to split them both and solve them both. So t minus 6 equals 0, t minus 1 equals 0. So t equals 6 and t equals 1. These are the two times when the particle stopped. Now, letter B wants to know, when is the particle moving to the left? For the particle to move to the left, that would be the same thing as the particle moving down. So the velocity would have to be negative. Okay, now I think this is the easiest way to go about doing this. What I'm going to do is I'm going to make a little number line here. All right, make a little number line. On my number line, I'm going to put 1, and I'm going to put 6, because at 1 and at 6, here's 1. Let's say here's 6 on my velocity function. You're at 0. So these are the places where it could change over, right? Okay, it could change over at 1 or at 6. So what I'm interested in is what's happening in between 1 and 6. So to do that, what I'm going to do is I'm going to plug numbers into my velocity function, and I'm going to pick some test numbers. Like, I'm not going to go beyond 0 here because it doesn't make sense to have a negative amount of time unless you're Marty McFly. Then I guess you could. But for most people, it doesn't make sense. So I'm going to pick numbers like, I'll pick a half, let's say, to test. I'm going to test these numbers. I'm going to pick, that's a half. I'm going to pick 2. That's an easy number between 1 and 6. Then I'm going to pick 7. And I'm going to plug them into V. So here's my velocity equation. All I care about is whether the answer is a positive or a negative. I'm looking for the negative answers. Okay, positive or a negative. So let's start with the 1/2. So V of a half would be 1/2 squared minus 7 times a half plus 6. Okay, so that's 1/4 minus 7 over 2 plus 6. So that's, and we can see what's going to happen here again. So you have 6 1/4. 7/2 is 3 1/2 as a mixed number, right? 2 goes into 7, 3 with 1/2 left over. I don't care what the actual answer to this is for the velocity. I just care that the answer is positive. Okay? I just care that it's positive. If I put 2 in, let's see if we can find some room. V of 2 would be 2 squared minus 7 times 2 plus 6. So that's 4 minus 14 plus 6. So that's going to be a negative answer. And if I plug 7 in, let's see if we can just do it here. We got 7 squared, that's 49, minus 7 times, it's also 49, so that's 0, plus 6, that's a positive answer. So when is the particle moving left? My velocity is positive here, so that means it's moving right. My velocity is negative in between here, so it's moving left, and then it's positive here again, so it's moving right. So that particle is moving to the left on the interval 1 to 6 in this interval right here. This one's good. These two, it's moving to the right, but I'm not asking you where it's moving to the right, so they're no good. That would be my answer on this interval from 1 to 6. Okay? All right. Now, how do I determine the speed of a particle? Well, remember, velocity is speed with direction, right? So you account for the direction as well as how fast it's moving. So determine just the speed. I don't care which way it's going, just how fast. You find the absolute value of the velocity. Okay, that's what the speed is. Now, there's a couple of things that you need to understand about the speed of a particle. One of them is how to calculate it with the absolute value of the velocity. The other thing is whether or not the speed is increasing or decreasing. So what you can do is think about a ball that you're throwing up in the air, okay? So you have this ball. The ball's being thrown up in the air, right? And then eventually it's going to come back down. But think about the speed of that ball as it goes up in the air. When the ball goes up in the air, the higher the ball gets, right, until it reaches the top, its speed goes down, right? The speed is slowing down of the ball as the higher it gets. Why is the speed slowing down? Well, that's because the velocity is positive. Okay, the velocity is positive because the ball is going up. But in the meantime, the force acting on it is the acceleration. That's gravity. But gravity acts down. Okay, gravity acts down. So the acceleration is negative. So when the velocity and the acceleration have opposite signs, one's positive and one's negative, in either way, the speed of a particle is decreasing. If velocity and acceleration have different signs. Now, for the ball on the way down, the acceleration is negative. It's still acting down, the force acting on the ball. But at the same time, the velocity is also negative because the ball's moving down. So now the acceleration and the velocity are the same sign. And then when the ball comes down, it speeds up. So the speed of the particle is increasing if the velocity and the acceleration have the same sign. Again, both positive or both negative, either way. All right? Okay, so now, suppose a particle moves on the x-axis. This is the same equation that we had before, okay? But the advantage is I can do it with just this one. Is the speed of the particle increasing or decreasing at t equals 2? All right, so to figure out if the speed of the particle is increasing or decreasing at t equals 2, I need to know two things. I need to know the velocity at t equals 2, and I need to know the acceleration at t equals 2. And then I need to compare their signs, SIG and S. So I'm going to have to find the derivative of this thing. So the first derivative of the position would be the velocity. And that's going to be, leave the 1/3, take the 3 down, take 1 from the power. leave the 7 halves, take the 2 down, take 1 from the power. Negative 6 is derivative of negative 6t, derivative of 5 is 0. So that's t squared minus 7t minus 6. That's my velocity function. My acceleration function is the derivative of the velocity. So the derivative of t squared minus 7t minus 6 is 2t minus 7. Okay, v of 2. So v of 2 is 2 squared minus 7 times 2 minus 6. So that's 4 minus 14 minus 6. So that's going to be 4. Let's just do this. That's negative 10 minus 6. That's negative 16. Okay, now if you're thinking, wait a minute, he got a different answer than he did on the previous slide. Remember, I changed the sign here from a negative to a positive. This time I just kept it the same. All right, a of 2 is 2 times 2 minus 7. So that's 4 minus 7, negative 3. So now, v of 2 is negative 16. A of 2 is negative 3. V and A are the same signs. They're both negative. So the speed of the particle is increasing. Why? Because at t equals 2, V and A have the same sign. That's your justification. You showed me the work, and then you justified it by saying at t equals 2. At this moment in time, V and A have the same signs, so the particle its speed must be increasing. And that's it. Okay, now, the only other thing I'd say is this. If I ask you for the speed at t equals 2, the speed would be 16, right? The absolute value of negative 16. And that's it. All right? And as always, thanks for clicking.